Yes, my name is Pengyuan Liu. I'm currently a postdoc at University of Helsinki, and today I'm going to talk about one of the early work that I did with my PhD advisor Stefano di Sabbata on the spatial autocorrelation analysis with graph convolutional neural network. Start with the introduction of the spatial autocorrelation. Spatial autocorrelation, in its most general sense, is concerned with the degree to which objects or activities at some place on Earth's surface are similar to other objects or activities located nearby, and its existence is reflected in the proposition which Tobler in 1970 has referred to as the first law of geography, that is pretty well known, that is, everything is related to everything else, but near things are more related than distant things. So when we're talking about the spatial autocorrelation, we're normally firstly thinking about the global measure of the spatial autocorrelation. The global measure of the spatial autocorrelation is to identify if there are clusters that obviously existed in a given region. For example, in the example slides here, we have positive spatial autocorrelation on the left hand. It's defined as positive spatial autocorrelation because we can say that all the similar values are clustered in the specific areas in this given region, while the negative spatial autocorrelation on the right hand seems to illustrated as a more random patterns in a given region. But apart from the global measures of measuring the spatial autocorrelation, we also have local measures. Local measures are developed to measure the dependence to only a proportion of area. Different patterns or process may occur in different parts of the region, and we normally define the autocorrelation happening in local statistical level using hotspot and the hotspot and the cold spot. And hotspot is a region where high values cluster together, and the cold spot is a region where low values clustering together. As an example map showing on the right hand, this is an artificial data set created for the hexagons, which this map, I will also introduce this map in my following slides as well. But as you can see here, this is an artificial data set, and all the high values seems to be distributed together, clustered together, and as well as the low value, for example, this part and this part. So we talk about the local spatial autocorrelation. So how local spatial autocorrelation is calculated is normally consists of two well-known continuous steps. The first step is to define the spatial weights. The spatial weights is to find the neighbors for each area in the given region. As an example showing on the right hand, and it can be visualized as a graph structure of the areas in a map. And we always have a lot of ways to define those spatial weights. For example, we can use well-known ROC continuity weights and Queen's spatial weights, but also we have other, for example, spatial distance way of defining the spatial weights. And then after defining the spatial weights, we normally perform the spatial statistics to decide the local autocorrelation. And we also have many different ways to do that, including local MONI and local GI or GiStar statistics. In this specific paper, we're using the local GI statistics to will be adopted in this paper. So the GiStar statistics returns each area in a given region as the z-score, and the formula is shown on the right hand of the slides. I'm not going to the detail of the formula, but it's basically calculate the z-score for each area in the data set. For statistically significant positive z values, the higher z-score is, the more intense the clustering of high values. For statistically significant negative z-scores, the smaller z arrow is, the more intense the clustering of the low value is, that is the cold spot. Sorry. So similar to many standard statistical analysis, interpreting the results of local statistics involving the expected values of the statistical model and in statistical inference, which often the p-values to quantify the significance of the z-value calculated by the local GiStar statistics. But in the recent years, existing studies in the discipline of statistical analysis identify that for very large data set, p-values will quickly go zero. And solely relying on the p-values will lead researchers to claim support for the result of no practical significance. So it seems that the p-value will be relatively robust for the smaller data set, but maybe less robust for a very large data set. In that sense, this raises to the questions of this paper is, can we conduct, for example, local spatial autocorrelation statistics on a relatively small regions and map those spatial patterns to a larger data set or the region? In this paper, we are adopting the graph convolutional neural network. It is a specific discipline in deep learning. We directly operate on the graph structure of the data. As in the spatial autocorrelation analysis steps, we need to define the spatial weights. And as mentioned before, the spatial weights can be understood as a graph visualization of the neighbors for each area. So the graph convolutional neural network has the potential to directly operate on this graph structure and has the ability to aggregate values for nodes from their connected neighbors. And in this particular paper, we adopt a semi-supervised graph convolutional neural network proposed by Keep and Welding in 2016, and it's a semi-supervised classification tool. By the term of semi-supervised learning, that means the graph convolutional neural network can learn from a small proportion of labeled data and do the classification on a large data set. So the overall framework is proposed in this slide, and we first of all taking the base map of Leicester, city of Leicester as a base map. So we will define the spatial weights for each area, each output area in this base map, and then we will conduct a small local spatial autocorrelation statistics on a small proportion of the areas and feed these two data into the graph convolutional neural network in order to classify the rest of the spatial patterns existed in this map. So for the labels, we're using GI statistics to identify the hotspot, cold spot, and the non-significant areas in this map. And we're still using those labels as the ground truth labels in order to evaluate the performance of this graph convolutional neural network. But it's important to mention that in this study, we're using the Queen spatial matrix in order to define the spatial weight matrix, and also we use the local GI statistics to decide the hotspot, cold spot, and non-significant spot. But they are all design choices. One can always replace Queen matrix to, for example, RUK, or replace the GiStar statistic with modern I statistics. It's complete up to the researcher's designing choice. So we experiment this framework on two data. The first data consists of 2,700 hexagons. And the reason to use the hexagons at the first experiment is because compared with irregular geometry shapes, such as output areas or the postcode areas, hexagons are the polygons closest to a circular shaped polygon that can be tessellated as an evenly space grid. Furthermore, their shape reduces the sampling bias that can emerge from the edge effects. So we use this, we consider the hexagons as a wonderful preliminary example to show our result. And we follow the method introduced by Mike Goodchild in 1986 to generate values to display in the local spatial autocorrelation, which is shown still on the right hand of this map, and we randomly selected 500 hexagons as the training sample. The meaning for that is that we will conduct local GiStar statistics on this randomly selected 500 hexagons and decide which are the cold spot, which are the hotspot, and which are on which areas is be classified as non-significant. And then we will train as those data as a training samples feed into the framework in order to learn spatial patterns for all 2,700 hexagons. The result shows that the graph convolutional neural network can achieve a really good performance in terms of the accuracy, and the visual comparisons between the result produced by the graph convolutional neural network and the local GI statistics are shown on the left hand of the map. Maybe show, and we can say that it seems that the graph convolutional neural network captured the spatial patterns relatively well. However, a more detailed visual comparison seems to indicate that our proposed graph convolutional neural network has some flaws. For example, as the circles pointed out, we can say that areas that has low values, which should be classified as the cold spot, and it is correctly identified by the GiStar statistics. However, it will be considered as non-significant in our graph convolutional neural network. Same to some areas have very high values, but is considered and is captured by GiStar statistics as hot spot, but they are considered as non-significant produced by our graph convolutional neural network. This kind of mismatch or the errors is quite interesting, and it's definitely worth our further investigations. And I do think they will be the key steps for us to improve our framework. And the second experiment is for irregular geometry. We're using a base map of Leicester, and it consists of 969 output areas in Leicester. And we use the same way of generating values. It is still an artificial data set generated for the whole map. And you can see the data distribution on the right hand of the map. Again, the accuracy in terms of the accuracy seems still very well, because it achieves over 95% of the accuracy, and the t-test between the results produced by the graph convolutional neural network and GiStar statistics seems to be correlated to each other significantly. But again, the visual comparisons seems to indicate that there are still many errors existed in the output of the graph convolutional neural network. And as I mentioned in the previous slide, it's definitely worth the further investigation into why these errors happened. For example, some in these comparisons, we can see some places has not completely low, but quite low values. They are considered as in GiStar statistics as not significant. But however, the graph convolutional neural network will consider them as the cold spot, and same as some relatively high values being considered as the not significant in the GiStar statistics, but produced as non-significant by the GCN. So they are this kind of mismatch or the errors are quite interesting, and will be the stepstone for our future investigations in this proposed method. So as a conclusion, we demonstrate that a graph convolutional neural network can capture the correspondence between the labels assigned through a classic local GIStar analysis and the spatial autocorrelation of the values by processing the data features. The spatial information so the result demonstrate that a graph convolutional neural network can capture the labels relatively well. And in our future work, we will test the scalability and the robustness of such a GCM-based method. We can test the method on a national, for example, national scales of England to say how GCM will perform in that sense. And also, we are aiming to develop a GCM-based framework that can solely independent from relying on the local statistics. So in this framework, we can say that we still need to use the local statistics to perform some first-hand analysis and use those assigned labels in order to classify the spatial patterns. But in our future, maybe we can use, for example, graph embedding-based techniques to directly generate those spatial patterns. The graph embedding-based techniques is a way still rooted in the graph convolutional neural network methodologies, and will create more spatial sensitive embeddings. So maybe we can use that. And further research, we will present those in the RGS and IBG conference in September, I hope. Thank you very much for your attention.
I was wondering, given that the GIStar and the local Moran and those different indices of autocorrelation are quite simple to calculate, what's the main purpose of using a graph convolutional neural network to predict those outputs? And when is a situation when you wouldn't be able to just calculate the index directly?
Yes. So, for example, as I mentioned in these slides, I mentioned that for very large data set, the statistical inference using based on p-values might not be that robust. So of course, when we do the local statistics on the scale of, for example, Leicester, that only consists of 969 areas, maybe you can say the p-values are still relatively robust. But when we conducted a larger scale of the analysis, for example, on the scale of England, maybe the p-values won't be that robust. So that is the reason why I introduced such a framework. So maybe we can do this local statistic analysis on a small proportion areas and map those spatial patterns on a larger scale.
I think in terms of the p-values question, that's maybe something you could talk with Chris Brunston and his colleagues about in terms of adjusting those p-values. Yeah. It's not really my expertise, but I know that they know a lot about that. So we have a couple of questions that have come through. So first of all, Phil Barty, I'm familiar with the Queen or Rook case when applied to raster data, but didn't quite follow how you were using it with a graph. Could you explain that aspect a bit more, please?
Yes, of course. So let's go for these slides then. So I'm sorry about this image though, maybe not that clear, but the weight matrix is a way to define the neighbors of each area in a given region, and it often can be visualized as the graph representation of the areas in a data set. So, for example, if we are considering well, it's often also visualized using the spatial the graph agencies in order to say if two areas are neighbors or not. And this is very similar to the graph structure of the data, because graph structure data also use the graph agency matrix in order to say if two values are the neighbors to each other or not. So this graph structure data will be fed into the graph convolutional neural network, which I mentioned in my presentation, that this network can directly operate on the graph structure of the data set. I hope this answers your question.
Nick Ham is the next question. So what window size did you choose for the GiStar and why?
That's a very details of the experiment. I actually can't recall at the moment. I need to go back to the paper to check the details. Yeah, I'm afraid I can't tell now because I forgot this details information.
Okay, I guess because we've got a few minutes left. Sorry, I introduced you as being at the University of Leicester, but you've moved on to University of Helsinki. That's correct.
Oh, just
so.
Yes.
Yeah. So, what are you working on now?
I'm working on a project to accessing the equalities of the suburban sports facilities, and my part of the duty is to analyzing the social media data to access the sports activities. Yeah.
Phil Barty has a follow up, so we'll just go to that one. So, the concept of adjacency is clear, but still not clear how you can define direction with a topological graph or data structure. Would have thought that Queen or Rook would need a direction component.
We construct such a graph as graph has the no directions. So for example, if area A is neighbor to area B, so there will be an edge added between these areas. And in the agency matrix, we don't define the directions, for example, from A to B or from the B to A.